This video is going to be about running a sample part with this angle head. And that's the company that makes it. You can read that. And this is a coolant powered. It's powered by the high pressure through the spindle coolant head running on this is a Mazak Integrex. And I have a job that's coming up that I can demonstrate this even a little better on. These people sent it to me just to demonstrate it on a video. All right, here's a sample part that I've decided to do, and it's just going to be an aluminum piece. I'm going to first bore the hole through it, or drill a hole, and then bore it out, and then we're going to run this groove, this groove, this groove, and this groove. So if we look at the simulation, I'm down with the angle head, and it's going to do this. It's a little bit hard to show on a simulation because maybe I can get rid of everything but the part here. So this is what the angle head's going to be doing. Just to mill these they're actually four grooves kind of evenly spaced around in the bore here. Kind of similar to oil grooves in a bushing. I was just checking the run out here, and I got about a 1/2,000, but that could be my collet, and probably is. I'm going to set this around about the middle of the run out, and I've already pretty much adjusted this with this carbide pin or carbide blank, end mill blank in there, up and down. So on this head, there's these screws here, and you can loosen this clamp ring, and you can turn it to get it pointing the direction you want based on where your spindle is sitting. Now, on this machine, of course, I have the ability to orient and clamp the tool holders as if it's a lathe tool in here, which is what I've done. I've clamped it in what they call the normal orientation in here, and I'm describing this as a lathe tool, if you will. Really, just basically an OD turning tool is the description in the tool setup, but actually there's going to be, of course, a ball end mill in here milling, but this is the only way you can get this machine to actually clamp the spindle in different orientations as if it's a lathe tool, and you have to describe it that way. And also, because this is a coolant powered angle head, I'm not going to be turning the spindle on, so I can do it this way. If this was say a normal angle head that you had with a normal one, you'd have to have a key on the spindle face here because you're going to actually run this spindle. And then just for the heck of it, I checked it this way on the front of it, like this. Get the indicator on it on the pin here. I'm going to jog the z-axis back a little bit. Now I'm going to set this sort of at the middle of the run out of the collet, which is somewhere about right there. And it looked pretty good going up and down this way. Okay. So now what I'm going to do, I'll take this dial base out of here. The first thing I'm going to do is establish this tool's length up to here, and I'm going to leave the pin in there for this because when I stick the ball end mill in there, it's going to be sticking out just very little, and I won't have any good thing to line up on, if that makes any sense. Well, you'll see in a second what I mean. So I'm going to use a pin. Let's see if I can do this somehow. This is kind of difficult to do because I'm working around the camera, and I'm also trying to jog the machine, put it in the finest jog rate. I'm just trying to feel some friction on this pin. This isn't that critical. I'm just doing a kind of a test part here. Test this angle head, and nothing super critical about any of this setup. But now that's a ½ inch plus half of this pin, which is a 1/4 inch, so it's 5/8 of an inch from the end of the part, the 0 point in this case. So let's go over to the control, the machine. This is tool 74A. Let's just look at the tool data just to make sure that which is here, there I should say, and you have what you call an A and a B dimension on here. Well, if I go over here you'll actually see it if I run the cursor. So the length A is the tool's length, and the length B here is the length from the center of rotation. Now, of course, this is not a a real turning tool, but I'm going to describe it like that anyway. So let me go back here and see. See, I have them set on 0 right now, so I could do a calculation. So if I go back to the position display, I got to take 9.9336. Let me go over here. I can't hold the camera and do this at the same time. I don't know if you can read that with the reflector. See if I can get a better angle. 9.9336 minus 0.625 for the pin and half the diameter of the tool equals. So we want 9.3086 in our offset on the tool. Let's go back up to the tool data. If I can do this. 9.3086. Can't remember 9.3086. Over here, push input. That puts that number right there. So now we should be sitting, which we are, at 5/8 of an inch, or 0.625 from the face to here. That gives us our dimension A, which is from here to our gauge line of our spindle for this tool. Now I have to take this pin out and put the end mill on there and touch something. I know the diameter of this stock and I've indicated it in, so I'll touch it on there, and we got to set the B dimension this direction. Now I've got this end mill that I ground the shank down because I had to shorten it to fit it in here, and I only want to stick it out just a very small amount. In fact, some of the flutes are going to be up in the collet a little bit, but it's got to be that way, or I got to grind a custom tool, which I didn't really want to do. So this wrench is kind of interesting. I don't know if you can see that. You see it has these, I kind of like this wrench. See, it has these kind of undercuts on it, and it hooks onto the undercuts on the nut on the spindle of the angle head, so it won't, you're not on here and it won't slip off. Kind of nice the way they made that. Make sure this isn't sticking out too far here. I think that'll be good. The bore that we're going into is 3 1/4 diameter, so this should leave me plenty of clearance for my program. Like I said, we're only milling down into the part half, or the radius of this ball, so that should be fine. I don't know if I can do this one-handed. Clamp it. Unclamp it, I should say. Clamp it. Alright. Seems like it clamped in alright now. Okay, now, what I want to do to offset this tool for the B dimension, I've got to measure it somehow. So what I'm going to do here is just kind of do this. Let me rotate this so I can get my hand in here. What I'm going to do is kind of touch this off on the OD here. Kind of awkward, but so I've got this thing on the center line, so wide this way on the bar, so I should be able to just touch this off with this pin by jogging it up in X until it just barely drags on the pin like that. Now Okay, let me get an exact measurement on that. Right here. 3.755, 3.756, we'll say. 3.756. So half of that, 3.756 divided by 2, because we're interested in the radius up here, plus 0.5 equals that, equals 3.378, if you can read that. I don't know if you can see that with the glare. So what we want to do is get the dimension on the machine to read that number. And the machine right now is reading 4.6075. So I'm going to store this number on the calculator in the second in B. Then I'm going to say 4.6075 minus memory B equals, so this number 2.2295, you can read that, I don't know, 2.2295 is going to be the number we want to enter in the control here for the B dimension, and go over to this entry. And what did I say? We want this at 2.2295. So 2.2295 here, input, and 2.378. Was that the number I said? Which is C. 2.378. Okay, so that gave us the dimension from the tip of that tool to the center line of the spindle, the milling spindle. So that should be offset more or less correctly, and it'll be good enough for what we're doing here, just a test program. I didn't really check the center of this direction of the tool in relation to the spindle center line. I'm not too worried about this for this program. It's not critical, but if I was doing a real job, I would have to check that. And on this tool offset for a lathe tool, you can set a wear comp in X, Z, and Y. So I could set that, and I can move it in any direction a little bit to get things lined up perfectly. But for the purpose of this part, I'm not going to worry about that. Now, I had one other issue with this whole setup was I'm going to set this out, by the way, before I run it for real on the part, but my stock was, it's in my program I defined this at 4 inches long, and this actual piece of aluminum here is about 100 thousandths, it's 110 thousandths less than that. So I'm going to set it, my offset in Z out this way, 55 thousandths, just to kind of center it in there so my milling doesn't go off the end of one of these on the bore here. So I'm going to go over to this work offset. I'm going to incrementally set that out 0.055 in the Z, like that. So that should be everything ready to run this. I've set the other two tools already. They're just a drill and a boring bar. Nothing critical with them. And I'm not going to show you that because it's just pretty much standard stuff there. Now I got to set up the camera and everything. We can run the first two tools. I'm just going to run straight in here and bore this out to 3 1/4 inches, just to bore right through this aluminum bar here. And then I'm going to set the offset intentionally out. I'm going to run this tool without coolant, because the coolant obviously makes this thing rotate, right? Coolant driven. You can't have any spindle speed command for the spindle here, obviously, because it's a lathe tool. It would give you an alarm on this machine anyway, and you don't need it because the coolant is going to power this. So let me set the camera up, one with the waterproof case and everything, and we'll drill and bore that out initially, and then we'll run this. We'll set the offset out like 6 inches out, And we'll run that program just to see that everything's working before we, and that we have clearance on the top of this when we go into the hole, of course. Okay, with the software Esprit, you get this additional piece of software that they call Esprit Machine Tool Builder, and with it, what you can do is take your adaptive items or even a vise or whatever, or you could even model a whole machine tool if you wanted to in this. But in order to make this angle head do what I want it to do, I got to tell the software in some fashion that it actually has a spindle on the end of this thing, and it's at right angles to the normal milling spindle. And so the way you do that is you bring this model, actually, by the way, I downloaded it right off the L-Tool website, so they already had the model for me. I didn't have to model it again. And then I have to define an axis of rotation here, which is like a spindle axis, so, and you can see it rotating there. And when you do all this, then when you mount the tool in the Esprit software, it realizes that there's a spindle here, and it'll treat this as a separate spindle. I don't know if I could shine some light, maybe up here. Finish doesn't look too bad, really. It's kind of weird because you can't hear the tool cutting or running or anything. Although I was being very conservative with the feeds and speeds because I didn't know what this thing would do. You know, it still rotates fine and everything. Doesn't feel any roughness or anything. You can't really tell or have a good indication if you're stalling the tool or not, or loading it or anything. It's kind of a little strange, but it does work, as you see. Let me take the part out of there and clean it off, and we can look at it a little closer. From the noise a little bit of the air compressor. I don't know if you can see the finish on the grooves, but they look pretty good. I haven't deburred it, I haven't done anything, polished or anything on here. Kind of interesting. I don't know if I can get up in here so you can see it. I don't know if the camera will focus that close to it. I'm just holding this GoPro camera in my hand right now. Kind of strange.